Hello everyone. In this video, we are going to discuss about the relation between current density J and the drift velocity Vd, and we will be discussing about mobility as well of class 12 physics from the chapter 3 current electricity. So here, I am just considering a metallic conductor, that is this yellow colored one. Let it be a metallic conductor. Then charges or electrons are flowing through this conductor, through this cross section. Let the cross sectional area be capital letter A. Vector E is the external electric field present here. L is the length of the conductor. Electrons are crossing this area of cross section A of this conductor with the drift velocity Vd. Let delta t be the time taken by the electrons to cross this cross sectional area. So, here to get the relation between the current density and the drift velocity, I am going to use the simple formula for the speed. That is, we know that speed is equal to distance travelled divided by time taken. Okay, so in our case, the speed is the drift velocity Vd. Distance is the the length of the conductor L, and I am taking the time taken as delta t. So that here we can write this as Vd equals, speed is the drift velocity here. Okay, so Vd equals L divided by delta t, or velocity equals displacement by time. That is also okay. Okay, so from this we can write L is equal to Vd into delta t. Okay. Now you see, the volume of this conductor V can be written as what? Length into breadth into height, LBH. See, length into breadth, that gives you the area. Height, it is actually the length of this conductor. No? When you keep this conductor vertically like this, the height of the conductor, that is actually equal to the length of the conductor. So, area into length. Okay, so volume can be written as A into L. That is, volume V equals A into L is Vd into delta T. So, this is the volume of the conductor. Now, you see, I am taking the number density as small letter n. Small letter n is the number density, which is the number of electrons in a given volume. So, small letter n equal to total number of electrons, capital letter N, divided by volume V. Okay, so from this you can write the total number of electrons as number density small letter n into volume V. Okay, that is total number of electrons is equal to number density small letter n into volume. What is volume? A into drift velocity into delta t. Okay. You see, this capital letter N, it is the total number of electrons passing through the cross-sectional area A. Now, let us consider the charge of one electron as E. If there are capital letter N number of electrons, then the total charge will be what? N into E. Okay. Now, you see, the current I can be written as charge NE divided by time taken. What is time taken here? Delta t. Okay, so I am going to substitute this n as this, which is small letter n A Vd delta t into E divided by delta t. Okay, delta t cancelled, so that you can write the current I as NA E Vd. So this is the expression for the current I. Now, what is current density? Current density J, this is equal to current per unit area. So what I am doing is I am taking this A to this side, that comes to the denominator. So we can write I divided by A is equal to NEVD. Okay, I divided by A, current per unit area, that is the current density. So we can write current density J is equal to NEVD. Okay, so you see, this is the relation between the current density J and the drift velocity Vd, that is J equals NEVD. Now you see, from this expression current density J equals NEVD, I am going to substitute this drift velocity as in the previous video we got the drift velocity Vd as minus EE by m into tau, where minus E is the charge of the electron. Here we have taken the charge of the electron as simply E. So we can write J equals n into E into drift velocity EE by m into tau. Okay, we just took the charge as E. Okay, we have not taken the charge as minus E here. That is why I am simply writing it as E. So this becomes what? J equals N into E square E divided by M into tau. Okay, now you see, we have from the vector form of Ohm's law, we have vector J equals sigma into vector E. That is, we can write J equals sigma into E, where J is the current density, sigma is the conductivity, E is the external electric field, the magnitude of the electric field. So from this you can write sigma equals what? J by E. Okay, see what is this J? N E square E divided by M into tau divided by E. So this E is like E by 1, so multiplication with reciprocal. So this becomes what? Sigma equals N E square E by M into tau into 1 by E, multiplication with reciprocal. Okay, E cancelled, so sigma equals N E square tau divided by M. Okay, see here we have actually two assumptions, that the relaxation time tau and the number density N are constants and independent of the electric field E. Now let us see what is this mobility. See, we know that conductivity arises from the mobile charge carriers. Mobile charge carriers means the charges which are able to move freely. In metals, they are the electrons. In ionized gas, they are the electrons and positive ions. In an electrolyte, they are the positive and negative ions. You see, mobility is represented this letter mu. And this mobility mu, it is defined as the magnitude of drift velocity per unit electric field. So magnitude of drift velocity, that is magnitude of vector Vd divided by the electric field E. So mobility mu equals, what is the magnitude of drift velocity? E by M into tau. Okay, divided by E. E cancel. So mobility is equal to E by M into tau, where mu is the mobility, tau is the relaxation time, E is the charge of an electron, M is the mass of an electron. Okay, tau is the relaxation time, which is the average collision time for electrons. So mobility mu, it is defined as the magnitude of drift velocity per unit electric field. So in this video, we have discussed about the relation between current density J and the drift velocity Vd, and we have discussed also about the mobility mu. I hope it is clear to you. Thank you.